Say my name.
Cause we want retribution. Oh yeah, we want retribution. Oh yeah, we want
Goddamn right.
retribution. Oh yeah, we want retribution. Yeah, we ran out of patience. Boil up with the cold hard hatred. I can feel the vibration. Feet in the streets, it's a new sensation. I wanna break faces on the...
Welcome back to the channel, everybody. It's been a long time. I've missed all of you. I hope you're all doing well. I hope you're in good spirits and good health. Today we're going to be talking about blind SQL injection. We'll be taking on the high difficulty challenge in DVWA. However, there's going to be some pretty significant challenges that we have to overcome. And to kind of preface this, I want to offer you all a challenge to help you all understand a key concept that we're going to be talking about later on. This concept is called a binary search algorithm, and if you've never been exposed to it before, it doesn't quite make sense at face value, but I think with the book example, this will go pretty smoothly. So if we consider this beautiful book, the IDA Pro book by Chris Eagle, if we consider this book like a giant array, right? So I know that's a little strange, but bear with me. Okay, so we're going to consider this book a giant array, and each individual page within the book we can consider an individual data element within the array. If we start at page 5, let's just imagine that this is the 5th data element within the array of the book. Okay, so let's say we want to find a piece of text on page, I don't know, 300 or something. Now the challenge is we can only turn 10 pages to get to the text that we want to arrive at, right? So there's a couple of different options of how we could traverse this book. We could do a brute force attack, and we could flip through each individual page, and maybe eventually we'll find page 300 and something. Or we can implement what's called a binary search algorithm. So before we can do that, though, we have to know the length of the array. So, if we kind of flip through this book, let's, for posterity's sake, we'll just kind of keep it simple. Let's say that, I apologize for the camera not focusing here. So I'm on page 636 right now. So let's say that we want to find page 274, but we can only turn 10 pages to get to page 274. So if we were to, kind of brute force our way to page 274, that would be a violation of our little challenge here. So how do we get to page 274 by only turning 10 pages in the book? Okay. So we know that roughly the length of the book is roughly 636 pages, plus or minus here and there. So what we do in a binary search algorithm is we first divide the array in half. Okay, so we've landed on page 291. That's roughly where we want to be. But this isn't exactly page 274. So what we do then, okay, is that we know page 274 is in the lower half of this array. So we'll take the lower half of this array and we'll split it in half again. So at this point, we've overshot our page 274, but now we know that page 274 is within the lower half of the segment that we've cut off from the array. So we repeat this process again. So this time we know that page 274 is greater than page 113. So we know that somewhere in the upper half of this lower chunk that we've cut off, somewhere in this upper half is page 274. And keep in mind, we've only turned the page, like once or twice so far. So we cut this in half again, and you kind of get the idea, right? So now we're at page 193. We do this again. We've turned the page 3 times. We've only turned 3 pages so far. Now we're on our 4th attempt. Okay, so now we're at page 261. And there we go. Page 274, and we've only turned 10 pages in the book. Well, maybe that's not the right way to say it, but ultimately we've only less than 10 flips, right? So this is a significantly faster way to traverse an array, but we have to understand there's some constraints here. We have to know the length of the array first, and we also have to know which data that we want to access. So that's going to be a key concept later on in this video. I hope that made sense. Okay, so this portion, we're just going to quickly cover the setup steps for our lab. Here I'm running a Kali virtual machine, and I'm also running a Ubuntu virtual machine. To get this lab started, we're going to switch over to the Ubuntu virtual machine, and we're going to install the docker.io package. Once we've installed Docker, we're then going to run this command, and this will allow us to start DVWA. So I've packaged all of this together in a simple shell script, and we just need to run the script. Now that DVWA has started, we switch over back to our Kali machine. We're going to open a browser and make sure that our DVWA instance is running. For the purposes of the setup of this lab, I've configured my host file to point to our Ubuntu lab machine as DVWA lab. So I'm just going to copy this, switch over to the browser, put this in the URL. Now, when you're getting this set up for the first time, you're going to be prompted for some setup steps to get the database set up for the first time. So I will enter admin and password. I've already set up the database, so we're just greeted with the DVWA main page. From here, we're going to switch over to DVWA security and switch the difficulty setting from low to high. Switch over to the SQL blind injection page. And if you remember the first two parts of this series, we had a place here in the page where we could enter some data and maybe inject some SQL queries. This time, we don't have anything that appears to be injectable. We just have a link here that we can click. And now we're redirected to a different page called cookieinput.php. This is what will allow us to set an ID cookie variable. So when we hit 1, we have a cookie ID set. So imagine our request is sending an ID parameter with the value of 1 to this page. And now we see that this user ID, which is supposedly this session ID cookie value that we just created via this link, that tells us that the user ID exists in the database. So let's try changing this again. Change it to a value of a user ID that probably shouldn't exist. And we see that we have the same Boolean-based logic from the previous two parts of this series. So we'll still be able to manipulate the database. We'll still be able to do some pretty cool injections on this. But we have some added stipulations. So let's look at the source code for the high difficulty page and see what's going on. So we do have a special cookie that is set on this page, and this is called an ID cookie, I guess. So imagine we have a cookie called ID, and the backend page will query if this ID that we've specified in this cookie, if that ID matches with a known first name, last name from users in the database. So we have a users table with a first name column and a last name column. And within the users table, we have an attribute called user ID. From here, we compare the user ID stored in the database with the value that we set via cookie. So our SQL injection is going to be based via a cookie instead of passing some SQL query directly into, maybe a text box on the page or a parameter in the URL or somewhere else in the request. So our injections are going to be done via this cookie ID. So that will present kind of a small change or a small piece of information that we'll have to be aware of. So we'll have to be aware that there is a separate cookie value for this attack. And if this user ID exists in the database, we will iterate through all of those, potential users. Will find this user ID, and if it exists in the database, we'll simply return some HTML entities saying the user ID exists in the database. But here's where this gets a little bit tricky. So if we inject something, if we inject an ID value of maybe a user ID that doesn't exist in the database, it will sleep for a random amount of time. So if you recall from the first video in this series where I raised some concerns about using sleep-based queries to enumerate the database, this is not exactly a good implementation or a good mitigation, but it does make sleep-based query injections impossible. So we will never be able to derive database information via a sleep-based query. If you imagine with every injection attempt that we make, we're going to get a response from the server at a random interval. So if we were to always do, like sleep 4, like we were in the first two portions of this series, if we were to inject sleep 4 and then try and enumerate different values from the database afterward, we would never be able to find out what the true value is that we are injecting for, because we'll always get that response at a different time than what we expect. To combat this, we're going to have to use that same Boolean-based blind injection approach that we've done in the first two parts of this series. We'll go from there. So thankfully, that is the only real mitigation that we have to deal with. So unfortunately, that's also going to impact our ability to return data from the database in a timely fashion. So while we're writing this exploit, we want to be mindful that we want to conduct this attack as efficiently and as quickly as possible. So to get around this weird little mitigation that's been implemented here, we're going to utilize a binary search algorithm so that we can retrieve the contents of our injected query faster than we would if we were to approach it linearly. So if you recall from the first two videos in this series, we use the ASCII and substring SQL queries to kind of traverse the database, and this would allow us to brute force the values of injected queries that we were submitting to the database. So as a quick review, the ASCII SQL query allows us to ask the database if a given record holds a certain value, and the substring SQL query allows us to traverse a given record from left to right. And if you recall from the first video, we use the substring command to pass in our injected query that we want the value for, and the substring SQL query will traverse the value of this injected query from left to right, one character at a time. So we'll be using the same logic today to combat this time delay mitigation, but if you think back to the book example where I explained at a high level the concepts of the binary search algorithm, we're going to need to know the length of our injected query first. So if you recall from the first two parts of this series, we often use the select user query to kind of, at the end of the video, say to all of us, hey, this was a bad query that we're injecting into the database. This is data that we should not be able to retrieve, where we would see this value app at localhost. So we can use the char length query in SQL to get the length of the query that we are injecting for. So in the case of select user, we're going to expect in DVWA that app at localhost is going to have a length of 13. So if you think about how we can implement this in Python logic, where you don't necessarily need to use Python, but if we're going to think about how we're going to implement this in exploit logic, we're going to want to be able to submit an arbitrary length to check for. So we'll ask for each individual query, hey, what is the length of this query that we are injecting for? And then for each position in that response, from left to right, one character by one character, we're going to ask the database if the first position in our injected query is equal to, for example, the letter A. So in this case, in our injection down here, we're asking the database, hey, we want to know the length of the select user query. And when we find the length of that query, we want to know if the first position in that response is going to be equal to the letter A. So this is going to help us build our binary search algorithm. But how do we go about doing that? So instead of asking, linearly, for each position that a given injected query could possibly be long, for any given length of an injected query, we want to be able to ask the database, is the first position less than, greater than, or equal to, if you recall back to our book example. So when we know the length of what we're trying to gain values for, and when we can ask the database at the same time, is this value that we're currently injecting greater than, less than, or equal to, this will allow us to derive this value in O log of n time, which is going to be significantly faster than if we were to traverse this linearly. So let's switch over to Burp Suite and see an example of this in real time. Okay, so let's see how this example works in real time. So we're going to open up Burp Suite, but before we do that, we're going to configure our browser to send all requests to Burp Suite with the Foxy Proxy extension. And we switch over to the Target tab, the Scope sub-tab. Copy the URL of the page that we're testing and put it into the target scope. Turn proxy intercept off. And to get started playing around with this attack vector, we're going to need to capture a couple of requests first. So we'll just simply repeat this process that we've already covered. Set our cookie ID value to 1. And here we'll simply just refresh the page. And this should be all of the requests that we need to start playing around with this vulnerability. So as you can see from our most recent request, we do have this ID cookie, and its value is currently set to 1. So we will send this over to repeater. And in the repeater tab, we'll just send this request off and double check that this was a successful request. So we see that the user ID 1 does exist in the database. So with blind SQL injection vulnerabilities, we don't get verbose error output like we do in normal SQL injection vulnerabilities. So what we will be able to do is ask the database, is the query that we are currently injecting, does that query evaluate to true or false? And with that Boolean-based logic, we should be able to derive database values for any injected query. To get started on this concept, we see that when we have a query that evaluates to true, we receive an HTTP 200 response from the server. So let's change this 1 to a single quote and see if we have a different result. And as you can see here, Burp Suite sort of seized up there, and that's part of the challenge with this particular problem on the high difficulty blind SQL page. Excuse me, the blind SQL injection page. So we saw that when we changed this cookie ID value to a single quote, instead of receiving an HTTP 200 response, now we see that we receive a 404 response. Furthermore, later on in the page, we see that the user ID is now missing from the database. So this should build our Boolean-based logic to conduct further attacks. I think an example that's going to make the most sense for everyone is if we stick with the select user query example. So in this particular injection, what we're doing here is we are asking the database what the character length of the return value of the select user query is equal to. And here we're basically asking the database, is it true that the length of the return value of the select user query is equal to 13? If that is true, we should receive an HTTP 200 response. If that evaluates to false, then we should receive an HTTP 404 response. We saw that this query evaluated to true, so how exactly does that work? If you think back to the first two parts of this video series where we use the select user query at the end of our exploit example to demonstrate to ourselves that, hey, we were able to successfully inject an arbitrary query into the database, and that returns the current database user. In the case of DVWA, that value is app@localhost. So the select user query for DVWA should always return the value app@localhost. So why would we need to figure out the length of this return value? So since we know the length of the return value of the select user query, that allows us to build exploit logic around each individual position for that length. So, for example, let's say that we didn't know that the value of the select user query was app@localhost. Let's say that it just returned some random string, and we have no idea what the value of that string is. So let's build off of this logic, and let's calculate the value app. So this will be the first 3 letters that is returned by the select user query. To do that, we'll stick with the ASCII substring injection method that we used in the first 2 parts of this video series. If you recall from the first 2 parts of this series, the ASCII query allows us to ask the database, what is a value held by a certain record? The substring query allows us to traverse the response of an injected query. So for example, it allows us to peel out a substring from a given string that's returned by the database. I hope that makes sense. So all of these queries combined will allow us to figure out what each individual letter for the entire length returned by the database for the select user query could be. So in the event of the first letter returned, so since we know from previous experience that the value returned by the select user query is app@localhost, we can use these queries in combination with each other to figure out what the value of the first character returned by the select user query is. So in that example, we know that the first character returned by select user is a lowercase letter a, and a lowercase letter a in ASCII is equal to the decimal value 97. So if we were to change our injected query asking the database if the first character returned by the select user query is equal to a lowercase letter a, we should expect that this injection returns true and that we'll receive an HTTP 200 response. And that was the case. So let's say that we don't know what the value of the next 2 characters are. So we'll change this number here to tell the database we're asking what the value of the second character returned by the select user query is equal to. So using our binary search logic, we know that each value returned by the database can hold one of 256 positions. So this covers the entire range of ASCII characters and even some invalid characters that go outside of it. So if we change this to a less than, we're essentially asking the database, is the second letter returned by the select user query within a valid range of ASCII values? So we would expect this to also return true. And it did. So to calculate what the actual value of the second character is, let's adjust our search space in half. So this should also evaluate to true. Now let's adjust our search space again, since we haven't found our value yet. We will calculate the midpoint. So for our example, the midpoint between 0 and 128 would be 64. We see that the database did not evaluate this query to true. We saw that we received what appears to be a false value, or a false evaluation of this query. So what that tells me is that somewhere between ASCII values 128 and 64 is the value that is held by the second character returned by the select user query. So let's adjust our search space again. This time we're calculating the midpoint between 128 and 64. So in our case, that will be decimal value 96. We should expect that this will evaluate to false because we know that the second letter returned by the select user query is a lowercase letter p, and that is decimal value 112. So we should expect this one to return false. So now we need to adjust our search space again. This time we need to calculate the midpoint between 128 and 96, and that will be 112 exactly. So this should evaluate to false as well, since we know that the second character returned by the select user query is equal to a lowercase letter p. What we're injecting here, the logic of this injection is essentially asking the database, is the second character returned by the select user query somewhere between lowercase letter a and lowercase letter o? And likewise, if we were to change this now to a greater than, we would be asking the database, is the value of the second character returned by the select user query between the characters lowercase letter q and lowercase letter z? Or I guess extending beyond that into the upper range of ASCII values. So we would expect this one to also evaluate to false. However, since we know it's not less than decimal value 112, and we know it's not greater than value 112, that insinuates to us that the second character is actually equal to value 112, which would be a lowercase letter p. So this should evaluate to true. So let's repeat this process for the third character. So far, we've figured out the first two values. The first one was kind of given to us because we already assumed that it would be a lowercase letter a. The second character we just arrived at via binary search type logic. So let's figure out the value of the third character using that same binary search logic. So here we're asking the database, is the third character's value returned by the select user query within the valid range of ASCII characters? This should evaluate to true. And we see we did get an HTTP 200 response, so let's adjust our search space by calculating the midpoint. This evaluated to true as well, so we will adjust our search space again. We received a false. So we know that the value of the third character returned by the select user query is somewhere between decimal values 64 and 128. So to continue this, we'll adjust our search space again. We need to calculate the midpoint between 128 and decimal value 64. So in our case, that would be value 96 again. So this one evaluated to false, so we know that we need to adjust our search space again. This time it'll be the halfway point between 128 and 96, which will give us a decimal value of 112. Okay, so once again, we know that somewhere between 112 and 128 is our midpoint. So to kind of fine-tune this binary search-based logic, let's take this a step further so that this really makes sense. So if we ask the database, is the value of the third character returned by the select user query greater than value 112, we should expect a false. So if we were to continue that, we would need to adjust our midpoint somewhere between 112 and 128. And we know that the midpoint between 128 and 112 is going to be decimal value 120. So we know that somewhere between 112 and 120 is our search space, or the value of third character returned by the select user query. So we could keep doing this ad infinitum until we eventually arrive at 112. However, we already know with such a small search space between 112 and 120, we would only have to do this only a couple of more times before our algorithm would figure out, okay, it's not less than 112, it's not greater than 112, it is equal to 112. So this should evaluate to true. So all of those steps combined allowed us to derive the value APP. Those would be the first three characters of the full value app at localhost, which is the value returned by the select user query. I hope that made sense, but if not, stay tuned. We're going to be writing an exploit around this logic, and when you see it in action, I think it'll really start to come together.
I'll be back.
Oh yeah, we want retribution. Oh yeah, we want retribution.